Okay, so we are all set. Okay, so as I was telling you, so there are, as you see, like in this discussion, there are two things that are coming up.
Sir, you are muted.
Sir, everyone is present.
Yeah, today I forgot to change the permission settings. So please be a little bit more careful. So today I just, before.
Sir,
So again
again
you
you
are
are mute. Sir, you can change the setting right now.
So I just again forgot. We have to go back, I think. Oh, where is that setting appearing? I just completely forgot.
maybe you should go to the participants.
Yeah, participants, yes. And then there is this meeting options, yes.
Sir, who can present?
Sir, save the setting.
Yeah, now it should be okay. So I have changed it.
Sir, you
So,
did not save it.
Also save.
Yes, sir.
oh,
No, no.
Sir, we are
okay,
still the present.
okay. So I think I did not save it. Hmm. So technology can be sometimes too cumbersome. Only me and then save.
Yes, sir. Now we are attendees.
Yeah, hmm. You should be so. Okay, so let's get back to where we were. Okay, so as I was telling you, so now you are able to hear me, right?
Yes, sir.
All fine. Okay, so as we were discussing, like, so there were these maps that we were discussing about, and like the two important mentions that always recur in the map are cities and the interconnections. Okay, so cities and interconnections or let me write a better English. Okay, so there are these two entities that are coming up. Okay, so these two entities actually make up the two basic parts of any graph data structure. So cities are in a graph realization, these cities are something called the nodes or vertices of a graph. Okay, and these interconnections are the edges of a graph. And for realizing a graph, both of these need to be supplied as inputs. Okay, so you remember I was telling you that there are certain data structures or certain algorithms where you need, where you have more than one input sizes. So this is one case. Okay, one nice example. Okay, so uh, just giving you a brief intro to the history of graph theory. So you know who was the father of graph theory, or who is the father of graph theory?
Euler.
Euler, yes. And what was his first problem which made him think about graphs?
So the seven bridges of Königsberg.
The seven bridges. Okay. So, and what was his question? Anybody knows what was his question that he asked?
Was there a path that starts from the same city and ends at the same city, passing all the bridges exactly once?
Very good. Excellent. So basically, the question that he asked is that, is it possible to traverse, this is a word that will recur multiple times in this chapter, traverse every bridge exactly once and come back. And do you know what is this called? This has a famous name.
An Eulerian tour?
Yes, this is called the Euler tour or the Eulerian tour. Okay, so now we will formally define a graph. So a graph typically denoted as GVE, okay, is a set of points better known as vertices or nodes, and a set of links that connect these vertices. Links are also termed as edges, arcs, etc. Okay, so V is the set of vertices and E is the set of edges. So basically, a graph is a collection of two sets. Okay, one is the set of vertices and one is the set of edges. Further, E is a subset of, so have you started uh, like relations etc in discrete math? Is that part started? Binary relations, Cartesian products?
No, sir.
No,
No. Okay, okay. But from your college day, I mean from your school days, you should be recalling what is a Cartesian product of two sets, right?
Yes, sir.
So
Yes, sir.
E is a subset taken from the Cartesian product of V cross V. Therefore, E is a set of dash. What?
Ordered pairs.
Very good. So remember graphs in terms of sets. This is a question that I often see people are asked in their final years, and they are not able, they fumble answering. So the best way to remember the definition of graphs is through sets. So edges are nothing but a set of ordered pair of vertices. Okay.
So,
So yes.
so can you please scroll it up once? Yes, sir. Sir, in the definition, like what have you written after edges slash, like links are also termed as
Arcs,
edges?
arcs, arcs, arcs,
Okay,
ARC, arc.
okay, 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 sir. Okay.
Okay. So it is always easy to represent graphs pictorially. Okay. Because we always are better able to think in terms of graphs if we draw them. Okay. So that's why, like, the best way to think about graph algorithms is to first draw example graphs. In many senior courses, especially related to graph theory, say you have this advanced graph theory course, you will see that many of the proofs that are related to graphs can be done just by drawing graphs and making cases for examples. So if time permits, we will see some of these in our tutorial lectures.
Sir,
Yes.
sir, why is it ordered pair?
You tell me why it is ordered pair.
Sir,
Can you
I
tell me?
think it should be
So here,
unordered
here,
if we are
here,
talking about set of.
here, say the edges are in this graph, the edges are I'll not write the others.
So does it mean UA is
Sir,
not
AB and BA.
Huh?
does it mean the ordered pair B comma A is not in the set E? Like are the edges directional?
So we will come to that. So let's slowly unfold. Okay. So basically, it depends why we have kept this definition as ordered pair is because we want to generalize it. We want to have a more generic definition, because if the ordering is lost, then one special type of graph we will not be able to represent ever. That is a type of graph that we will talk about in a moment. Okay, and you will see why there is this necessity of having an ordered pair. Okay. So before that, let us try to discuss, and in this particular discussion itself, it will be somewhat clear, and then we will make it further clear in the next few definitions. Okay. Undirected edge. So these type of edges are bidirectional. In nature. What does this mean in terms of ordered pair? And this will answer your question.
They can be unordered.
AB directed edge. Edges that are unidirectional. In this case, okay, so this is why we kept the definition open, so that we could accommodate the definition of both undirected and directed edge in one single definition. Now, given the type of edges, you can have two realizations of the graph. One is the undirected graph, which is a graph having only undirected edges. Other side of the coin, directed graph. A graph having only
Sir,
go ahead.
sir, can we have a graph which contains mixture of these two edges?
No, no, that is by definition not allowed.
Okay, sir.
So can two edges intersect? Like, can we have a edge between AD in a undirected graph?
Absolutely. So here there is one very important question. So may I know your name? It's a very important question that you have asked.
Venkat, sir.
Venkat. Venkat, so and for all others, graph is not a geometric structure. It's an abstract data structure. Do not mix it up with a geometric data structure. There are special kinds of geometrically like specifiable graphs, which are called planar graphs, where you can actually embed the graph in a plane. Okay, these are special types of graphs called planar graphs, about which you will read in when you go for like I think like some portions of this is also covered in discrete math. I'm not sure, like when I used to teach, I used to cover it. If not, then if you take the advanced graph theory, there they will cover. So that's an elective, but if you take up that course, there they will cover. So in general, graph is an abstract data structure, okay? There is no geometry associated with it. So any crisscross, everything is possible. However, there are special notions of graphs where we are interested in a embedding of the graph in some space, in some geometric space, okay, starting with planar graphs. So there, like we are interested in the geometry of the graphs. So remember this very clearly. There is somebody on unmute. Okay, so now after this, we will also try to introduce ourselves to a few um, like handy definitions which are used or which recurs in many different algorithms. Okay, one of these is called a complete graph. So a complete graph is a graph, as the name suggests, where every node is connected to every other node by an edge. So in an undirected graph, of n nodes, say an undirected complete graph of n nodes, what is the number of edges possible?
N choose 2.
choose 2.
NC.
NC2. Next is regular graph. So a regular graph is a graph in which all nodes have the same number of edges going out of them. Okay, so every node, say, has k edges going out of them, then it will be called a k regular graph. This has a special name. We'll talk about this when I talk about the definition of that special thing. Okay, for the time being, you can like consider that the number of edges going out or like connected to a node is same for all the nodes in the graph. Then this is a regular graph, and if the such number of edges is k, then we call it a k regular graph. So what about a complete graph? Is it a regular graph?
Yes, sir.
Yes, sir.
What regular?
N
If there are
N
n
minus
nodes,
one.
it's a n minus 1 regular. It's an n minus 1 regular graph. Weighted graph. So a graph is said to be weighted if there are some non-negative values assigned to every edge of the graph. So typically, this weight represents some sort of a cost. So again, coming back to our initial example, suppose A, B, C are cities then these edges are representing some sort of connection, and the cost might be the cost to travel, or it might be the cost to lay roads between the cities. Okay, there is some notion of cost, or it could be the distance between the cities. So some notion of cost is actually expressed by the values on the different edges. And that is where the utility of a weighted graph comes in. Outgoing edge. A directed edge is said to be outgoing from its origin vertex. Incoming edge a directed edge is said to be incoming on its destination vertex. Degree. The number of edges connected to a vertex is called its degree. So guys, this part is like a lot of definitions, and it is kind of unavoidable. If we don't do these definitions, like most of the things that we follow up, the algorithmic things that follow up will be difficult to follow. So that's why my suggestion would be, so this is what I tell all the students over the years. This part is a bit monotonous. Make a table, okay? And like for all of these, have a one-line definition with some example. So like you used to do in your schools. So make a table where you have all these definitions in one place, so that like, you can keep referring to it. I mean, for the first few occasions, you will see that these are a bit confusing, but then like things become very easy. So now with a lot of practice, we don't need to really look into those table charts. But for the first time, like you might need a table chart for a few days, and then it will become, and that's kind of one of the best ways to remember these definitions. And always think of a picture or a diagram of the graph. Okay, immediately things become much more clear. So that K, and try to connect things. That K that we were talking in the regular graph context. So now do you realize what that K is?
Degree of each edge,
Yeah, K is the
each node.
degree of each node, not edge. Is the degree of each node. So another way to express the definition of a regular graph is that in a regular graph, all nodes have the exact same degree.
Sir, is it necessary that the degree should be always greater than 0?
Yes, it is a very good question. This is a very good question. So now, uh, before we talk about degree greater than 0, less than 0, let us think like what is the minimalist construction of a graph? So I told you that a graph is a collection of two sets, right? V and E. Now, as you know from your school days itself, that sets can be empty. Now try to make a guess. I'll tell you the answer, but make a guess that which among these two sets is more important and without which existing the graph cannot exist. What do you
Vertices.
think?
Vertices.
Vertices. Vertices. So for a graph, the vertex set has to be non-null. Edge set can be null. Okay. And if this is so, may I know who asked me the question? That whether degree can be 0 or not?
Sir, it's Neeraj.
Neeraj. Okay. So Neeraj, now tell me, like, if I tell you that V has to be non-null, what is the minimalist construction of a graph that you can do?
Without edges, only having vertices, so that k can be greater than or equal to 0.
Uh, without edges,
We
and
only can
how
have
many vertices are required?
at least one.
One vertex, right?
Yes.
So the minimalist construction of a graph is a single vertex. So you are digressing me to more interesting stuffs. Anyway, it's good to discuss and clarify the concepts. So now, see,
Sir?
in this graph, yes,
Sir, here V is not an ordered pair. It is just a value, right? So
yes, V is not an ordered pair. E is an ordered pair.
okay.
E is a set of ordered pairs,
So can we call
which
that
is chosen from,
as a vertex?
huh?
Okay, sir, and understood.
Okay. So now,
And sir, one more doubt.
yes,
Sir, if
can
there are two
I
nodes,
finish this? Wait.
okay,
Can
sir,
I
okay.
finish this and then otherwise I'll forget what I wanted to tell and then
Okay,
you
sir.
come back with your question. Keep your question. I'll come back to you. Okay. So now, so a single vertex is a minimalist construction of a graph. Now for this graph, Neeraj, do you see like what would be the degree of a node?
0.
0. Okay. Now tell me like a little bit generalized construction of the graph with no edges. The graph has no edges. So you can have some n number of nodes, right? Here also, degree of each node is 0, right? So these type of graphs where you do not have any edge but only nodes, that is the graph has all nodes with degree 0. These type of graphs are called degenerate graphs. Yes. Now let's get back to your question.
So now it's clear. I was asking about the same thing, that can there
Yeah.
be nodes without any edges?
Yeah, I knew that you will be asking this. Okay. Because I also as a student used to ask this similar type of question. So I recall my student days. So now, since a directed graph has directed edges, in a directed graph, you have two types of degrees, the in degree and the out degree. See, some of these you don't really need to, have difficulty to recall. Some of these are clear from their names itself. So in degree, what do you think should be the in degree?
Incoming.
Number of incoming edges.
Number of incoming edges. That's why we defined incoming and outgoing edges earlier. Number of incoming edges. Similarly, the counterpart, number of outgoing edges. Now, in addition to this, there are a few more things. Parallel or multi-edge. See, this type of graphs we really don't deal in our day-to-day algorithms, but still, from a graph theoretic purpose, it is good to know. So a parallel or a multi-edge is a kind of edge where, so it's defined as follows: two undirected edges having exactly the same end vertices.
Sir, if it's undirected, then how are we calling anything as end vertices?
These two are multi-edges. Okay. So both of them are like having the same endpoints. So these are called parallel edges or multi-edges.
Sir,
Hmm?
sir, that then in the set of edges there will be exactly same two elements. So is that allowed?
Yes, yes, that is allowed in this kind of. So this is now becoming a. That's why I called it multi-edges. This is a multi-set now. Very rarely used. So in directed graphs, the definition changes a bit. So two directed edges okay, having the exact same origin and destination. Vertices. So sometimes we also call this the source. It's either the source or the origin. Okay, so here there is a catch. So these two are parallel edges.
No, sir.
No. Okay. So this is something that people often get confused, and that's why I drew it. Okay. So this is a parallel edge. And what is that edge? Anybody knows?
Anti-parallel.
Antiparallels? Okay, let me not draw such a big graph. Let me draw a small graph. Because I want to make the end of this class a little funny. Okay.
Sir, sir, how do you denote
Can,
the
can
set
I
of
can I finish this and then we talk? These are the two nodes. Now tell me what would be this edge? Think the most appropriate name.
Rejection.
Antiparallel.
Rejection. See, you are already so low on note.
Friend zone.
And such edges are called reciprocal edges. Yes. Now coming back to your question. What was your question?
Sir, I was asking like for the previous graph where you said that the parallel edges. So how do you denote the set of those edges?
Same, like it's a multi-set now. Typically, so when I am using a parenthesis, note the notations. When I am using a parenthesis, this means undirected edge. When I am using a square bracket like this, then this is a directed, sorry, an angular bracket like this, then this is a directed edge. And here you just repeat 2 times. So if you have the angular bracket edge repeated 2 times in the set, this means that you have a parallel edge.
So, but in a set having the same element multiple times, the same thing.
That's why I said it's a multi-set. Go back and brush up your like like the advances in set representations. So search with multi-set in Google and you'll get. I think you'll get enough information.
Okay, sir.
Sir, hello. Sir, is it
Yes.
possible to have an edge between the same vertex, like source and destination?
Yes. That's the next definition. So self loop, okay, an edge that starts and ends on the same vertex. Or when its endpoints coincide.
Sir, can you say that name again?
Yes.
Sir, can you say that name again? Setup.
Self loop. Self loop. Self loop. Looping on itself.
Sir, so we cannot have reciprocals for this. It will always be parallels if we have that.
So reciprocals and parallels are same here. So a simple graph. So this is our day-to-day graph. Huh? This type of graphs is what mostly occurs in most of our applications. So a simple graph is a graph that neither has self loops nor parallel edges.
Sir, can you please scroll a little bit up?
Adjacent nodes, when there is an edge between two nodes, they are called adjacent nodes. Incidence. An edge between vertices V1 and V2 is said to be incident on V1 and V2. Now the next few definitions that I'll talk about are pretty important from the algorithmic side also. Okay, so these are some of the things that you might encounter in various algorithms and you might be asked to find them out. Okay, and these definitions are like, again I'll make a tabular chart for this so that it becomes easy for you to remember, but before that let's get introduced to them. So do you want to do this today or should I start tomorrow afresh? Let's start and then we can recap tomorrow. The first one.
Sir, is incidence a synonym of edge?
Huh?
Incidence is
No,
synonym of
no,
edge.
no, 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 no. Say this is a edge. So this is like an incident ray. Okay, sometimes edge is also called a ray. So basically, this edge E1 is said to be incident on the node A. This is what is incidence.
Sir, if it is outgoing, then also we call it incident.
This is for an undirected graph only.
Okay.
Okay, so the first one, walk. So a walk is a finite alternating sequence of vertices and edges always beginning and ending in a vertex, or let's say in some vertex. Closed work. A work which begins and ends on the same vertex is called a closed work. Else, it is called an open work. So here V1, E1, V2, E2, V4, E3, V3, E4, V1 is a closed work. Path. An open work in which no vertices are repeated. Length of a path.
So do we need to mention E1? If we are going to V1, then we can only go through E1. So what is the necessity?
Huh?
So do we need to mention E1, V3, E1, V1? Why is that E1?
Yes. Yes, it is of course necessary. Imagine that there is another node like this. Okay. And there are
But
edges.
yes, sir. But if we are going to V1, then there is only one edge E1.
Yes, of course. Like in this case, it is fine. So I don't understand your question. Typically, what you do in when you do a program, you express each of these as again an ordered pair. Okay, and therefore you don't need to write it in this way. So you just write V3, V1, V1, V2, and so on. You can do it that way. But I don't really understand your question about so is your question that why am I writing this E1?
Yes, sir. Can we directly
Otherwise,
write one V2?
V1, V2, and then
V3, V1, V2. That's it, sir. That is the path.
V3, V1, V2. Is that the path?
Yes.
Then what will you do? This is one counter example. There can be many such counter examples. Another counter example, so even if you consider it to be a simple graph, There could be other counter examples. If you are considering a path.
Sir, in that case, we will write a V3, V4, V1, V2. Shouldn't we do?
V3, V4, V1. Yes, of course you can write that. Of course you can write that. You can write that, or you can, so typically path will be, as we said, it's an alternating sequence of edges and vertices. So you have to specify that whether, so okay, I understand. Like you are telling that if it is a simple graph, you don't really need to mention the edge label. But if it is not a simple graph, then you will have to mention the edge label. So if you have to have a generic definition, then you need to have the edge label. Okay.
Okay.
Okay, so we'll stop here. Next day we'll start with length of path.
Sir?
Yes.
So these definitions like walk, closed walk, these are defined only for undirected graphs or also for directed graphs where we have direction.
You can have a directed version of many of them.
Okay.
Okay. Path, etc. You can immediately see that there could be directed definitions. Okay.
Yes.